just recently. I forgot. Okay, guys. So we are going to move on to another module in this course, which is about the waves mainly. However, just to follow the whole syllabus and just to give you a good background on how to take care of waves. So it's actually a very good stop to take a look at oscillations first, right? And that will be the keys of today's lecture. We're going to look at oscillations, okay? Plus, once we sort of understand this one, actually, we're gonna have a chance to revise what we did with the Newtonian physics. So we are going to do some mechanics again, but the perspective that we are going to look at is going to be something that actually going back and forth. And once we have that, then we are going to couple that oscillation to some other things. And it turns out there will be a way that you can transfer. You can think of it in terms of like the propagation of energy or disturbance or whatever, and that will generate waves consequently. So that's what we kind of like tie these two together. The oscillations will be the first thing that you need to understand the mathematics, how to describe something that sort of go periodically in time first. And once we sort of have that sort of underlying idea in place, then moving on to waves, it's going to be like sort of like additional stuff that you put on top and complete the whole pictures of waves. Okay, sounds like fun. Okay.
Okay.
Who knows? All right. So what we are going to do today is going to be simple harmonic motion. Maybe I think many of you have already done this before. And the results that you are going to see today is going to be something that looks quite familiar to many of you. Okay. However, we're going to look a little bit deeper just in case that some of you haven't seen this or haven't had a chance to analyze this kind of motion before. And the story about waves and all this stuff will come later next week. Sounds like a good plan? All right, let's dive into it, guys. I'm going to start. Today is going to be a pretty light lecture because I'm going to ask you a lot. Because the reason is for this is like, if I just go through all the stuff by myself, I mean, I can get it done in like maybe 10, 15 minutes and, you know, might not so kind of like sure that you guys understand the whole picture of this. So there are one actually big key points that I want you to get today. And if you can get that one, I think that sort of like accomplish the whole main goal of today's lecture. And that is, how do you describe the oscillation motion? That is the key.
Okay.
All right, that's the main key. So let's go back to something that's quite simple. You have a simple system of mass with a spring. Yeah. Very good, very good. And every time that we talk about the spring, you know that it's follow Hooke's law. So let me write on the side, force on the spring is just negative kx. And then when you say negative sign there, it means you look at the vector equations, right? So that means when x is positive, force is going to be in the opposite direction. So let's look at this scenario right here. Look at the position of the mass. The mass is in a positive x direction. So that means you're going to have the spring try to pull this thing backward. Okay. On the other hand, when the mass is at zero, there will be no springs force. That's fine. And then when the displacement go negative, in this case, the spring will try to push to the right, opposite all the time. So let me write this just to confirm. The red arrow, that is your x vector, displacement vector. Red arrow here is the displacement vector. Cool. All right. So the force vector in Hooke's law over here will always point in the opposite direction to the direction of the displacement, which is fine. So far, so good. All right. My green arrow here is exactly as the blue arrow in the text. I mean, in the figure right there. Okay. Now, my point is this, guys. Give me equation of motion. So from the sound of it is the equation that eventually is going to govern how this mass is going to move. Okay. How are you going to write that? Easy. Every time you look at this one, you do sigma F equal to MA. There you go.
Okay.
Right, back to mechanics stuff. So in this case, you look at the free body diagram of the mass. You look at it, it's just like Ajahn, because we assume that there's no friction on the floor, there's nothing here. So the only force that acting on this mass is just spring force. So that's it. My sigma F is just that negative kx right there. And because this is a motion in one dimension, so that means I can just put it as an m times x component of the acceleration. So it means everything is going to be along the x-axis. Sounds good? So far, so good. Guys, this is it. Equation of motion is right here. You are done.
Okay.
And the amazing things about this is, from this equation alone, you will be able to predict how this mass is going to move. Whenever, wherever you want, it's on here. I mean, everything is already laid out to you, okay? So if I rearrange this equation a little bit, and I just leave the acceleration on the left and move everything to the right, and you can treat this one pretty much like just like a scalar equation now, because everything is only on the x-axis, so you don't have to worry about. Well, when I say scalar, it's kind of unfair a little bit, because I mean, x still has positive and negative side. So it's actually, it's one dimension. Let's say this is a single dimension equation. So the acceleration is a negative k over mx. So far, so good. But then you guys remember this one, that the acceleration is the second derivative of the displacement. So that means I can replace this one with the dx by dt 2 times. Yeah. And that's arrived me this equation right there. And now I'm going to rearrange one more time, if I want to make it look something like equation on the right with the triple stars equation there. But wait, that's my point. Here, when you look at this equation, what are you seeing? That replacement of the omega stuff that comes later. That's fine. But I'm just asking you, what is this? Of course, you say about that. It's a differential equation, because what left-hand side, you have derivatives of x. The right-hand side, you have the variable x. So this is just a kind of differential equation. The question is, have you learned how to solve this equation before? Let me sort of give some feedback right here. Have you done this? Maybe it's supposed to be like calculus 2, I guess, because if you do the calculus 1, you only do like derivatives, integral, and other stuff. But then when you want to treat differential equation, you probably do the calculus 2. All right, so you guys know how to solve this second order differential equation? Yes or no? Yes or no? No need. Yes. All right, quiet means good. All right, so no feedback means yes. Okay, so if you don't want to go back that far, you just, Ajahn, I kind of like learned it, but I kind of like forgot it already. Do we need that? We have to go back to studying that, you know, solving the second order differential equation again? No. Think about this. I'm going to need extra page here. And let's see if you guys got to follow my idea or not. All right, try this. If I have just a simple equation that look like this, second derivative, do you know the answer of this equation? It looks simple now. Oh, my handwriting is bad, sorry. Oh, what did I do? Oh, okay, there you go. All right, let me write it one more time. Okay, d2x by dt2 equal to x. Just this, just like second derivative of x equal to x. Do you know the answer? All right, stick with me. All right, it's gonna be slow today, but it's gonna be a lot of fun.
Okay.
I don't know, it might be, it's my approach. It might be annoying to some of you guys. All right, so when I read this equation, because this equation looks pretty plain simple, it's just asking you what kind of function or what kind of x that get differentiated twice and gets itself back to x. What do you think? What kind of x is that? So first thing first, you probably think in your head, if x is going to be some polynomial, when I say polynomial, let's say like x cubed, x fourth, you know, or x itself, that's bad. The reason it's bad because when you do dx by dt, right, you are pretty much gonna, well, when I say dx by dt, that's Okay, let me write something like this, right? So if x is going to be, if my bad, sorry, I swapped the uh variable over here. It's supposed to be function of t. Sorry, my bad. It's not function of x. So x, that's what we want. Okay, sorry. So if x is just some power polynomial of t. So the bad thing about this one is every time you do differentiate, your power get reduced, right? And if you do it twice, it's going to get even smaller, on and on. Not good. Okay, so the polynomial stuff, the power function won't work. It's not going to be a solution of this equation. So this is no way.
No.
Then you think about it, you go back in time. Since you start beginning studying mathematics, what kind of function do you have other than power functions? Now you start thinking, yeah, it could be not polynomial. Then what else? It's going to be what? Trigonometry. There you go. So you say that could it be sine? That's kind of not good because dx by dt, derivative of sine, you get cosine. Second derivative of this, you get negative sine. You don't get yourself back to the original because of that negative sign thing. So no, this doesn't work. What else have you learned? Of course, another class of its function is exponential. Let's do with e to the x. Yeah. So when you do e to the x, e to the t, I would keep right e to the x, sorry. So dx by dt is going to be e to the t. d2x by dt2 is still e to the t. And that is good.
Okay.
See that? So exponential function is supposed to be some kind of solution of this. So that's why you can expect x somehow supposed to be in exponential form somewhere. But of course, there'll be some generality of this one. You have to, put any kind of e to the x into this to be a solution. But at least you know that it's supposed to be something that looks like exponential. That is going to be the answer of this equation. Sounds like a good plan here. So let me compare and contrast this with this. What if you have the 2x by dt2 equal to negative x? Now you know what to pick because Ajahn is here. This is a dude that get differentiated twice and get itself back with the negative sign. Perfect. That's what we want. So we know it's going to be the sine thing. But then you just realize that cosine works too. See, so this is part of the reason why mathematics in whatever, elementary school, middle school, high school, everything, you have to study power function, you have to study exponential function, trigonometric function, logarithmic function, because eventually it's going to be useful later, and later is now right here. Okay.
Okay.
Now, with this idea in mind, you'd even know that Bajan, sine and cosine seems to work. Both of them works. So what you probably learned before back, for those of you that already took the calculus 2, the sum of the two is still a function that is a solution of the differential equation. So that means to make things general, so what you can do is you just have the addition of these two will work. You add these two things, that is fine. Okay. Plus, if you're going to multiply this thing with a constant in the front, that doesn't change anything. Plus, there's so many plus here. If you want to add some extra stuff behind the t, it doesn't change any derivatives. I will show you what I mean by, let's say, if I write my solution to have a shape of a sine t, just start with this first. So you can see that I take derivative once, I get a cosine t. I take derivative twice, I get negative a sine t. See, I get the original back with the negative sign in the front. So my a sine t is supposed to be a solution, but that's not sort of like not general enough. I can do it one more time. I say, Ajahn, what if I have a sine t plus a little bit of stuff? You do derivative once, you still get a cosine t plus a little bit. And you do the chain rule, but the chain rule doesn't give you anything extra, so that is fine. And then you do a derivative one more time, you get negative a sine t plus delta. Woohoo, perfect.
Okay.
So this one is also a solution, but this looks even better than this. So I think this is okay, not good enough. Let me discard this one. This seems to check. With me? And then the good thing about this one is, well, now when you look at this, well, done. That's kind of nice because I kind of memorized briefly that when you have sine A plus B is sort of like, well, sine A cosine B plus sine B cosine A, right? Something like that. So at least you have some trigonometric identity that you can use. So that means by having this T and delta in there, that means you have two terms in it. And if you want to spread this one out, what you're getting is going to be sort of, this one is A in the front, sine T cosine delta plus sine cosine T sine delta. Whew, look at that. It's perfect. Perfect in what sense? It's perfect in the sense that we already wanted both sine and cosine to be in the solution because they sort of like have equal thing. You can pick either sine or cosine. They are actually the same function. So this is good. So by adding that extra delta into it, you actually automatically adding both sine and cosine as part of your solution. And that's what you wanted in the first place. So you see where I'm going at. So conclusion is, this is it, guys. The solution to this type of equation, this type means that second derivative equal to the negative of the original function, gonna have to be using either sine or cosine function. Cool?
Okay.
I don't know if this sort of like give you a good enough introduction of everything, but that's what I'm doing over here. So let's come back to our slide over here. But Adan, this is what we want. The second derivative equal to the original with the negative sign. Perfect. Sine and cosine will both work. But then the thing is, you still have this extra k over m come into play. And that's kind of annoying a little bit. But Adan, wait a second. This one, you don't have anything in front of x. So that's fine. Those sine t and cosine t seem to work. But what if you want some extra constant in the front? Well, that's fine. What you can do is you just manipulate this solution a little bit. And how can you do that every time you differentiate and then you get something in the front? Okay, almost done, guys. Stick with me a little bit. I know it's kind of like what I'm doing over here, but the whole truth is going to get revealed right now. So imagine this. If I have just simple A equal, I'm sorry. Why just redo so much? Okay, if my x equation over here is equal to A sine, now you just add some number to it. Let me call that number to be just whatever A here, T. Every time you do the derivative, you get A cosine AT, but then you have to do the chain rule, right? So the chain rule, you need to do this dAt by dt one more time. And this term give you extra A. So at the end, you get mini A, big A, cosine AT. One more time, you do the derivative again. You take derivative, small a, big A just stays there. Derivative of cosine, you get negative sine AT. And then you do the chain rule again. The chain rule will give you extra A. So that means what you get at the end is going to be negative A square A sine mini AT. But the A sine mini AT is just the original. So that means at the end, what you get is a negative A square X. You see what I'm getting at?
Okay.
So what I'm saying over here is, if you have a constant in front of T, that constant in front of T, constant in front of T, when you do the second derivative, that constant will come up in the front as an A square. Perfect. That's what we want. So if you come back here, well then you have this constant in front of X. So it must be the square of some numbers. I mean, some parameter. And then allow you to just, okay, let me name this one to be something square. And let me call that omega square. Sounds like a good plan. Got that one? So this is the reason why you rename this one as the omega square. And once you have this, you know right away the final answer of yours, the solution of this equation is going to be, it's either sine or cosine, and you allow constants in the front, you allow another constant in the parentheses. So what should be the final conclusion of this whole thing that I'm trying to explain to you guys? Solution that looks most general possible, and is going to be the general solution of this, is going to be some number, sine or cosine, then you do omega t plus 5. That's it, guys.
Okay.
With me? That's how you pretty much kind of like get to the solution of this one intuitively. I don't know if it's intuitive or not, but at least it gives you an idea that the only solution that will allow you to solve this kind of equation, second derivative equal to itself with a negative sign and allow some constant multiplying in the front, is going to have a shape like this. And now you're not going to have to confuse anymore. If you read some textbook and that textbook say the solution of this one look like this, you're not going to feel a thing, because either sine or cosine is fine. And you know now, because by having this omega t plus phi in there, you have a combination of both sine and cosine built into this expression. Isn't that cool? And that's, to me, that's kind of like, it's a fantastic stuff of mathematics. Just starting from simple equation that look like this, you know right away what should be the solution that look like this. And what kind of solution is this? You already learned the sine and cosine function is the periodic function. And that means this starting equation that we name equation of motion allow you to explain the movement that go back and forth of the spring. And that's perfect.
Okay.
We have oscillation in energy. And because this oscillation give you only a single that we are going to explain later, it's going to have a simple structure. We're going to call this simple harmonic motion. Why is simple harmonic? I will reveal right now. All right, but up to this point, any comments? So far, so good? Okay. I don't know, is it a confusing way of introducing this or not? But if it's good, then I'll just keep going. All right. Okay. But I hope it will get better. All right. So stick with me. Will the completed slide be on go? Oh, yes. Oh, thank you. Yes, I forgot. I told you guys that I'm going to post the noted. Okay. I forgot to do on the second and the third, right? All right. I'll do that. This written note will be up on the Google as well. All right. For those of you that want to, you know, just gonna crack some codes, my handwriting codes. Okay, guys. So if you sort of get a sort of like an idea of this is where we are going, now we are going to try to interpret this. Okay, now we know the form of the sort of like, you know, final solution to this. So here we go. There. Now we will start to, you know, dive into it. What does it mean? So if you see the solution that look like this, it's going to be fine. So this one, good. This is good. This is good. Yeah, you know, this is allowed. When I say allowed, mean this is supposed to be one of the possible solution of that. But what does this mean? First, look at the left. Is x as a function of t. So what this one says is trying to say, where is the position of the mass as a function of time? So when you're writing something like this, so what I'm saying over here is, you guys know that the cosine function never go beyond 1, never go below -1. So at least you know that the x max is going to be positive a, and x minimum is going to be the negative a. Make sense? So that's why we are going to name this one amplitude. And amplitude just means the maximum displacement that the mass can move. So it show up right here. The peak and the bottom appear at positive and negative a. Done. Second question. The omega that we decided to give the name to that k over m, right? The omega square. What is the unit of omega? What is the unit? So when you look at this one, Majan, is omega times t. Is omega times t. Whatever that comes after cosine function, exponential function, logarithmic function must have no units, because it will be weird if you have some units behind those. It's called like transcendental functions. Like you never ever have sine of mg before in your life. No, never. It's never happens, because we know that mg has a unit of Newton. Sine of Newton will kind of, okay, what is going on here, right? So this one, no way. So that means that is already give you a clue that omega must have the units of 1/2, because time is already in the unit of second. So the omega is in the unit of 1/2. But wait, you know even better. So you guys knows that every time that the time move on, okay, move on and make omega t equal to 2 pi. When omega t equal to 2 pi, you already complete one cycle in the cosine or sine function. You guys with me?
Okay.
Okay. So that means actually the time that it takes for you to have the omega t equal to 2 pi, that is going to be the time that you take the oscillation to complete one's perfect cycle. You guys with me? So we are going to rename that one to be period. And this one is going to sort of showcase something that looks familiar to you. Do you remember this formula a little bit? Yeah.
Okay.
Omega is 2 pi over period. Yeah. Actually, it's the same definition of the angular velocity or speed, if you like. Yeah. That's what it is. So actually, the angular speed or angular frequency, that is the meaning of the omega right here. Cool. It's frozen. What's going on? My screen doesn't want to move. Oh, here we go. All right. I'm getting a new internet at home. I think the only problem is the carrier that I have, they haven't upgraded the line, so I'm not. All right, you guys, I'm back. Oh, sorry. It's shut down on me. Oh my God. Weird. This is the weirdest. Last 2 minutes, it's gone. Okay. All right. So I'm back. Okay. All right. Thank you for the comments saying that I'm muted. Okay. So I'm getting a new internet. Yeah, I just realized that the maximum speed that I got is only like 40 meg or something. They cannot upgrade the fiber optics or whatever around here, so I cannot. And I think because people just like work from home or other stuff, so we are sharing the bandwidth at this point. So I think that's why things getting worse and worse over time, right? And this is way worse than I never had this problem before back in the previous trimester or whatever, but now it's the worst. All right, guys. So let's come back here. So now we kind of know that omega is 2 pi over period. And this is exactly what you defined before. You can name this one angular speed, or you can talk about this one as the angular frequency if you are looking at the circular motion. But if you look at something that's spinning, you can define it as like the angular velocity with the right-hand rule and all this stuff. Does that make sense? Okay, so actually it turns out there is a reason that why we rename this to be omega, because it's actually give you the angular frequency, and it's gonna link directly to how fast this thing is oscillating. So perfect. So let me give you a conclusion. So the omega is in the unit of 1/2, but to be fair, I mean, because we have the 2 pi factor in it, it's supposed to be radian per second. And everyone knows the radian is no units stuff. Okay, so conclusion that we have over here is omega is 2 pi over period. So the omega will give you the frequency of stuff. And everyone still remember the period is just the inverse of the frequency. So you can also write, okay, let me conclude the whole thing, 2 pi f, 2 pi over t, up to you. Use one. Cool. All right, then. So that is giving you what the A is, what the omega is. And now we know A is amplitude. Omega is just the angular frequency. Now, if you really want to add some extra to it, just like what we said, but Ajahn, actually you can throw in some, extra constants after the omega. So we kind of know what you're doing over here is you look closely here, X is a function of time. So if you look at X at t equal to 0, look at this. Once you substitute t equal to 0, it's just saying that where would you want to start? At time 0, when you start the clock. Yeah, it's at phi right there. So you might be able to call this like an initial angle.
Okay.
But then people don't like angle because when you talk about angle, you talk about like geometry. We are not doing any geometry. So we tend to have another word. We're going to use the phase. Okay. Introducing phase. But anyway, phase is just angle. Right? But actually, it's just giving you like it's the angular position. So you rename it as a phase. But yeah, that's what it is. Okay. Usually you can interchangeably use angle. I think everyone will understand. Okay. So that's initial phase. Or you sometimes might be sort of like heard of this one as a phase constant, because it's just a constant that you add on top of the omega t, all right, which is something moving in time. So that's it. So when you have that extra phi there, is just saying that at initial time, when you start the clock, you just want to start where? So compare the figure on the right. The upper one, that is the cosine omega t, right? You guys with me? Okay, that is the A cosine omega t, is this yellow curve right here. That's good. So now when you have A cosine omega t plus phi, all you have to do is you just slide your yellow curve over there and you just slide it to the left a little bit. Or you can imagine that what you're looking at over here is just like, think about it. You can name this one like, okay, this is 0 angle, the phase equal to 0. And everyone know every time you complete one cycle, that will equivalent to 360 degree angle. With me? Or you can call this is 2 pi. And everyone you go half a cycle right there, that is going to be 180, half a cycle, and that will be pi in the radian unit. Okay. So now you start to see that, oh, Ajahn, I can, slice this one off and I can name this 90 degree. That is pi over 2. I can do this. This is going to be 270, and that is 3 pi over 2. So now with this idea in mind, then now you can adjust anywhere you like. You can imagine that you start from 0 and the angle start to increase in the position 1, 2, 3, 4, 5, 6, 7, and until you get 90 right here. 91, 92, 93, 94, all right, you get 180 around here. 181, 182, 180 here, 270 here, and 271, 272, all the way to 360 right here. You complete one cycle. Make sense? So that means every position on this curve will associate it with an angle. Does that make sense?
Okay.
So if I say, hey, there is a delta right here, or the phi is just at that angle, phi is just there. So when you add that phi there, that means I just said I want to start this curve at that point. So that's why it's just exactly the same thing as I slide this curve to the left until that point. Let me put the black dot there. That point is right here. Oh, yep, that's it. You're done. See that? The connection here, the black dot. Let me write it big here. There you go. That is your phi position on there. And that's what it means by the phase. Because now you can use that angle, which is a phase, to specify the position on this curve. And that's why we name it like an angular position, because by knowing the amount of that angle, you know exactly where on this sinusoidal curve that you are talking about. Whew. All right. And that's pretty much, I think that's everything about the mathematics of something that is oscillating. Isn't that cool? I don't know. Is this too long of something that I'm talking about? But if you understand this whole thing, understanding waves will be half or 50% easier. But if you don't understand this whole, it's not mechanics. If you don't understand this whole infrastructure of the oscillations or sinusoidal function, getting into waves business next time is going to give you some crazy stuff that will sort of build on top of confusion. We get you even more confused. Even though, to me, once you understand this whole thing, everything is very simple.
Okay.
I need to use this word simple. The reason I say it's simple because once you understand the mathematics of this one, everything will look just like it's a recipe. It's like a cookbook. Okay, you know how to read this one. You just follow the instruction and you get to the final answer straightforwardly, seriously. Okay, but the obstacles over here is just you don't, get what the detail is behind this whole mathematics right here. Okay, guys, any comments so far so good? Give you some, something to talk about here. All right, so if this is good, then what do we get here? Okay, and then I'll give the summarized before the break one more time. But what I'm getting over here is this, guys. So the conclusion is, here we go. Now we understand from now on, for the rest of your life, every time that you have a simple harmonic equation of motion, which looks just like this, derivative of x twice equal to negative something square x, you know right away all the time that solution will look just like this. I put a triple star over here. This is it. This is the solution of this second order differential equation. Plus, now you understand, if you read some textbook, and if the textbook would like to call this one as a sine, who cares? Nobody cares. Sine and cosine function are equivalent. It's just you translate 90 degree, you get the sine. You translate another 90 degree, you get the cosine. You translate another 90 degree, you get another sine, cosine, back and forth. So to me, sine and cosine are exactly the same thing. And with that addition of the phi, that's how you manipulate sine and cosine. Get back here. Look at this. If I slide the curve until I get the curve that has the shape of this one, the blue, that is already sine. With me? Okay. So that's already sine omega t. See, so that's how you translate cosine, turn it into sine. And if you start with sine, you translate, you get cosine along the way anyway. All right, cool. And what you're getting over here is this. This is the solution. So it means it's telling you exactly when this mass supposed to be at any time that you want. You can plug in 1 second, 10 seconds, 100 seconds. You will know exactly where the mass should be. So this is x as a function of time. So once you know x as a function of time, you now are able to calculate the velocity. Simple. It's just the first derivative of x with respect to time. You differentiate once, you get negative a omega sine omega t. Whatever in the front give you the maximum value possible. So you know right away that omega a will be the maximum velocity attainable of this system. Cool. And then you keep going. But If I want acceleration, you do derivative of the velocity one more time. You do dv by dt to get to acceleration. You do the derivative of sine, you get cosine. You do the chain rule, you get extra omega. So now you get omega square a in the front. Negative sign has to be there because that's from our beloved negative sign from the differential equation. And now we know that omega square a is going to give you the maximum possible acceleration. So that is your a max. And you are done.
Okay.
Got that one? This is simple harmonic motion. Mass is in oscillation. You know exactly where it's supposed to be. You know how fast it's going to move. And you're going to know its acceleration at any time. And the reason that we call it simple because all of this oscillation happens with a single frequency, omega. Now, when I say frequency, and then I talk about omega, everyone understands that I'm talking about the angular frequency. But if every time that you would like to calculate the pure frequency in second, then you just say omega is 2 pi f. You can link omega to f easily. Or if somebody comes in, well, hey, I want to know the period of motion. How long does it take for this mass to oscillate one complete round? You do omega equal to 2 pi over t. You are done, guys. This is it. This is everything. I said, like, yeah, people always use this one, like everything you need to know about simple harmonic motion. But actually, that's probably not the truth. All right, that's probably not everything, but at least this is the fundamental stuff that you need to understand. Oscillations that is doing something simple, and that simple oscillations using this equation of motion, we call this simple harmonic motion. And you are done.
Okay.
Cool? All right. After the break, I think this is a good time to stop here and then just, have some time for your brain to, absorb this whole thing. All right. And after the break, we'll look at some, applications and things that allow you to understand a little bit more about. Once we know this, what else is that? What is so good about this one? Okay. You probably have learned this one already before in high school, but then we're going to go a little bit further, and that is after the break. All right, guys, take 10. So what we are going to start the sort of like the, comparisons of what we just studied with other system. Let me ask you this. Hey guys, could you write down the equation of motion of this pendulum thing? You have just a simple pendulum here. You have a mass attached with a string. The string is attached on the ceiling or whatever. And then in general, of course, once you pull the mass up from its equilibrium just a little bit and let it go, it's going to swing back and forth, right? Write down the equation of motion for me. Woohoo! Give it a shot right there. No clap, no clap.
Okay.
Guys, give me the equation of motion. All right, and you guys just said about that is already on the slide. Okay, think about this one. Okay, you have a mass. There's a string pulling this mass up. Okay, so you just write down the free body diagram, of course, that's what you're trying to do. And then you just say, okay, you're going to have a downward force that, let me write on top of this one, that is your mg right there. And of course, you're going to have a tension, try to pull this mass up. Okay, let me just draw it on top of that right there. And because right now, your direction of motion turns out to be in this direction right here. If you look at one particular moment in time, okay, so that line is too big, but that's what it's about. So I'm just going to draw this one again, a super, super light one here. Okay, here we go. So at this particular moment, you can imagine that this mass is sort of like it's swinging, right? It's trying to go from right to left. But anyway, the point is at this particular moment, you can think of it like the tiny time, the mass is sort of like moving along that tangential line. Make sense? So this is the reason why you are pretty much have to take this line to be your sort of like your guide or your reference. And you just draw, it's pretty much like the coordinate system, if you like, okay? And then you take this coordinate system to be your reference. Whatever the vector that doesn't fall into this coordinate system, then you try to break them into components. And that's what you get. All right. So you have the mg that is pulling down and it's not on your axis right there. So I'm just going to break this into two components there. And once you're done with that, then I'm just going to get rid of the original. Okay, I don't need that anymore. All right, so your mg, break it into mg sine theta on the left and mg cosine theta on the right. Okay, and the key is because this mass is supposed to pretty much going left, the tension and the mg cosine theta are supposed to cancel each other out. So at least you get an equation say that magnitude of the tension is going to be mg cosine theta. But that doesn't do any good for us because that only say that the mass is not going to move up or down along this y-axis of us. So the only thing that's going to keep this thing moving is that mg sine theta. All right. So what I'm going to do is we're going to say this is our tangential direction. So total force that acting on this one is just the tangential direction of the force. So that's why the subscript T is right there. And it just, when you want equation of motion, you just use Newton's second law, sigma F equal to ma. And because right now your sigma F is only mg sine theta, and that's you're almost done. You just substitute mg sine theta there. However, don't forget, even though this one looks just like a scalar equation, but it's not. It's always a vector equation. So when you look at this one, you can think of it like, okay, Ajahn, I'll keep this positive side to your right-hand side, just like, normally you do it with the x-axis. So that means the mg sine theta is actually pointing backward. If you take the s to be the distance that you are coming from the equilibrium point. Do you see this? This s right there? Okay, so what you are saying over here is it depends on the distance from the equilibrium. Equilibrium is already on the vertical axis in the center. So when you pull it out, okay, that is your positive s direction, but the mg sine theta actually pull this thing backward against your positive axis, positive direction of yours. So that's the reason why you have the negative sign right there. So far, so good, guys? Okay. Second thing is, because you are interested in the displacement along the circumference of a circle, and at any time you learn from mechanics, that's, I forgot to turn on the video. My face is missing, but that's all right. Okay, so what you have before back in the mechanics days was just every time that you have any mass moving, the velocity is going to point in the direction tangential to the curve, right? Or the line of motion. That's exactly what's happening right here. Okay. So if you would like to get the acceleration of that one, all you need to do is just take the derivative of that s. You will get the acceleration that you want. So that's why that's the equation of motion right there. You are done. Minus mg sine theta equal to ma, and your acceleration is to a tangential acceleration. So it's going to be the second derivative of s with respect to time. And then what? Do you see what you are getting at this point in front of you? From the look of it, it looks nice and cool, Dan, but it's kind of like it's a mess. So let's rearrange this term a bit, shall we? Mass cancel. That's good. So far, so good. So let me rewrite the equation just like what we had before. So I'm going to pull d2s by dt2 to the left. Whatever left, just leave it on the right-hand side. No, Adan, it doesn't look good. On the left, you have second derivative of s. On the right is a function of an angle. But then, is there any relationship between s and the theta? Well, yeah. Adan, if you look here, you will see that you have a triangle that you can sort of like, locate here. Yeah. It's not a triangle, it's a segment of a circle right there. There you go. Okay, so when you have this, Bhutan, yeah, so there must be a relationship between the theta and the arc length within this sector over here. There you go. There. All right, there you go. So when you look at this relationship between the theta and the s, you can right away can see, Bhutan, that's fine. from definition, theta is an arc length over the radius, and the radius is just the length of this string right there. Cool. So that means you can write S as a product between theta and L. And if you want to do derivative of this one, doesn't matter. You just take derivative with respect to time on both sides. L stay fixed. The length of the string doesn't change. Or if you want to do the second derivative of S with respect to time, that doesn't do anything to the L. So L stays there. The only thing that you get is just the second derivative of theta. So that means you can pretty much write the second derivative of S in terms of the second derivative of theta. And that's give you, follow me here so far, theta by dt2. So far so good. And there is an L right there. Almost done, almost done. And when you see something like this, let's keep second derivative to the left-hand side, move everything else to the right. Does it look good? No, Adan, no. Even though it looks almost good, but it's not. There is a sine theta on the right. And on the left is theta, but on the right is sine of the theta. Wouldn't it be nice if I can just get rid of this sine theta? The answer is yes. And if you remember, this is a simple harmonic motion, right? I'm sorry, this is a simple pendulum, right? And if you remember back in the day of high school physics or whatever, if you have a simple pendulum, and if you want to have a swing in something very simple, you usually have a requirement saying that the sine theta, okay, it's supposed to be dealing with theta that is small. So theta is supposed to be small. The reason for that is because with the small theta, you can approximate sine theta to be just theta. This is the reason behind it. The reason behind it, because once you're dealing with just only small theta, sine theta can be approximated as theta. And then you end up with this equation right here in yellow. And that looks good.
Okay.
Does it look good to you guys? Well, yeah, Dan, this is exactly what we want. Do you see now? It's exactly what you saw before back in the mass with spring. Right there. Same. Oh, it's slow. Give it some time. Never happens before. Okay, here, see? Derivative of the function that you want, okay, equal to the negative of itself with some constant in the front. See? Remember this? And compare that to this. You can see right away that it's a derivative, second derivative of theta equal to itself. You get theta back with some constant in the front. Once you see this, you can pinpoint right away, Ajan, I got it. This is my omega square. Or what you can say is omega is root G over L. And what I'm saying is you don't need to do any mathematics anymore. I can write down the solution of this second order derivative right away. I can just say, here, I wrote right on the side here, hey guys, solution theta as a function of time is going to look like A, sine or cosine, your pick, omega t plus 5. And I'm done.
Okay.
Isn't that amazing? Wow. This is wow, wow, wow. So from now on, every time that you have this kind of equation, you're done. A simple harmonic with a known angular frequency. You know how fast it's supposed to oscillate by saying that the omega is supposed to be square root G over L. So the only way that you can change the frequency of oscillation, you either change the G, you move to other planets, whatever, move to different elevation, you change the gravitational acceleration G, or you just adjust the length of the string. These are the only two ways that you can manipulate the omega. So this is a reason why if you're swinging in just like a single, on a swing that you play in the, you whatever playground or whatever, and then you don't change any length of the string, no matter what you're trying to do, you will oscillate back and forth with the same omega all the time. Right? That's what it is. But I mean, our point in this lecture is you see the general or the common shape of the equation of motion. That gives you the simple harmonic motion. Isn't that cool?
Okay.
Okay. And once you have that, you don't need to do anything anymore. You're done. You know the omega, you move on with your life. You know this, you move on with your life. No need to go back to mathematics anymore. The table that I'm showing you here is just give you the idea of how small is the theta that you allowed to approximate sine theta to be about theta. And as you can see, when you go up to about 10 degree, your error is getting about 0.5%. So that's why in general, they will give you like a rule of thumb saying that as long as you have a simple pendulum, that the swing, the maximum angle that's oscillating back and forth is within like 10 degree, it's still acceptable. But at least now you can see that the actual pendulum, when you swing at the large degree or the large angle, is not simple harmonic anymore, guys. Isn't that amazing? All right, so that's something that for you to understand, that because the real equation of motion, there is a sine theta on the right side. So you actually have to solve this equation to get to the equation of theta. But because, I mean, to solve this one, you probably need like a numerical calculations using computer or whatever. So we do some approximation, and then we can still treat this as a simple harmonic. That's the whole key.
Okay.
All right, guys. So I think that's a good conclusion about the simple harmonic in the simple pendulum case. Make it so simple. Okay. All right. And this give you a small angle approximation. That's very useful. All right, here we go. Now, your turn. Another system for you to try. And I will try this with the simple harmonic that happens in some object that now has sizing. It's not just like a point mass anymore. Now you have a mass that extended in size. You put a pivot there, you hang it over and then move it from the equilibrium, let it go. It's going to oscillate back and forth. Everyone knows this, right? Write down the equation of motion for me, guys. Go ahead.
Okay.
All right, because now it's an extended object, so you need the second law, the Newton's second law, but in the form of the rotation. Okay, so you do the torque equal to I alpha. Does it sort of give you any sort of like recall back some memory here? Total torque equal to I alpha, and everything is in vector format. Here we go. Cool. Now, look at this one. You see, you have to calculate torque first. Okay, and if you remember, torque is, okay, go back here, R cross F. That is your torque right there. But because right now, the only force that acting on this one and give you the torque that turn this mass is going to be just an mg. So the R cross F, if you look at this one, is going to be, if you take just the magnitude of this, it's going to be the size of the R, the size of the force, and the sine theta. Or if you memorize this one as a R times F, but then R is going to be the R in the perpendicular direction. You guys remember this one?
Okay.
Yeah. So you just try to find torque, and torque is a product between the force and the distance from the force to the point of rotation. And then whenever you talk about the distance from force, it means it's the line of force. When I say line of force, mean you look at this one, and then you say, about Ajahn, force is acting along this line right here, the green line that I'm drawing right now. So if you want to take the distance that we're talking about is going to be the distance between O and here. Okay, let me put the red color here. There you go. Yeah, that's a distance. That's a R, perpendicular directions from the line of force to the pivot point. Okay, cool. So far so good. All right, so if you know that the CM that the mg is acting on is at a distance d from the pivot point, So the torque due to this mg is going to be, okay, let me write torque is going to be mg, that's a f, and the distance r perpendicular is going to be d sine theta, where the theta is the angle in the middle right there. So far, so good. All right. So once again, so I know now the magnitude of the torque due to this weight or the mg is just mg d sine theta. But now here comes the thing. All you need to do is just take this and equate to the angular acceleration. And because you already defined the theta, so you know right away this is going to be the second derivative of theta with respect to time. So far, so good.
Okay.
Now, the last thing is this equation is going to be a vector equation. So think about this. So when you look at this one, you move or you pretty much bring this mass to the right side a little bit. So you are pretty much rotate this mass this direction. You guys with me, right? So you swing this mass to your right shoulder, right, to the right side. So you're moving in that direction. But then look at the torque. The torque is trying to pull this mass to your left. So if you remember about the second law of the Newton's second law in rotation, you have to use the right-hand rule, right? The omega, the alpha has to follow the right-hand rule. So look at the theta. You swing this mass or you rotate this mass to your right. Use your right hand, curl your forefinger in the same direction as my black arrow right there. Your thumb will point toward your face. So that theta over there is pointing to your face. Let me put the dot right there. You guys with me? Your thumb point to your face. And usually it's something that's sticking out. You can call this a positive direction. I mean, or negative, doesn't matter. But you just say, okay, the direction that's sticking out from the screen, that's your positive direction. Look at the torque. The torque is trying to pull this mass clockwise. So if you use your forefinger and curl your forefinger in the same direction as this torque is trying to pull this mass clockwise. So you move your forefinger clockwise, your thumb point into the screen. So actually the torque acting on this mass is pointing into the screen, and that is your negative direction. You guys with me now? So I think you remember vaguely, I hope, about when you have to decide the direction of those angular parameters, right? The velocity, the acceleration, or the angular displacement. Everything has to follow the right-hand rule. So this is the reason why your theta positive is the one that's sticking out from the screen. So that means the torque that we calculated, the magnitude mgd sine theta, need,
Okay.
negative sign. Okay, and that's what it is. I'm done. That is your equation of motion. But then everything based on the Newton's second law in the rotational form. Total torque equal to I alpha. And what is I? I is the moment of inertia of this whole extended mass right here. So far, so good, guys? All right, this is your equation of motion. Now, solve this equation, guys. All right, let's do this with me, shall we? So I can rearrange this. Let's keep d theta by dt2 on the left-hand side. Everything that's not, I move to the other side. I have negative mgd over I sine theta. And once again, you can sort of guess what's on. I can see it now. If the theta that you are sort of like moving this mass is not that big, so you're still working within the small theta regime over here, you can approximate this equation to make it look like mgd over I theta. And what do you see, guys? Woohoo. Do you see what I see? Yeah, Adan, is simple harmonic again. I can just write down the equation right away that your solution will look like a sine or cosine, your pick, omega t plus phi, and you are done.
Okay.
What is omega? Omega you extract from here, that is your omega square. So that means your omega is the square root of whatever that stick in front of that parameter or the variable theta. So your omega is square root mgd over I. And that's it. See, simple harmonic. You are done. See, so from now on, even though you try to apply this one to a more complicated scenario, however, if at the end you can arrange your equation that look like this, you can conclude it's a simple harmonic with a known omega. Seriously. Okay, so that's the nice or the beauty of this whole thing, that once you know the structure that's govern the simple harmonic motion, and one day if you see it, oh, Dan, it looks exactly the same, right away, that's it, you're done.
Okay.
You know right away it's going to be simple harmonic motion for sure with a known angular frequency. Isn't that nice? I think that is pretty much give you like 3 scenarios to compare, right? And everything just go back and forth, back and forth. If it's a spring, now. If it's a pendulum, if it's a mass, that's fine. Okay, and this is kind of like give you, just give you some reflection of this formula over here. You can feel that, okay, that makes sense. When the omega depends on what factor, okay? So that's make it cool that you can analyze the behavior of the frequency by based on the omega. Yeah, root k over m, root g over l, square root mgd over I. They're all giving the same simple harmonic motion. Cool. All right.
Okay.
Okay, so toward the end of this, all right, what I would like to talk about is just, I would like to talk about, what about, now we know everything. Unbelievable. We know where it's supposed to be, how fast it's moving, what is the acceleration. So once you already talk about the position and velocity, one thing that you can talk about right away is its energy. And you are like looking at only 2 kinds of energy. Let's go back to the case of the mass on a spring. The velocity, and once you know that when the mass has velocity, it has kinetic energy. So it's 1/2 mv squared. Same thing, it's mass on spring. So you know the spring constant K, you know the position, you know that you can calculate the potential 1/2 kx squared. And if you want to figure out the total energy that's already in the system, it's just a summation of the 2. You take the kinetic energy plus potential energy. But this is the beauty of it, because you know exactly how they are going to move. You take the velocity square, you guys slide back a bit. We have already figured that out here. See? Okay, oh, I used the green, but that's right there. Okay, right here. So the velocity is negative a omega sine omega t. And the x itself is a cosine omega t plus phi, whatever, plus dot plus I, doesn't matter now. So what you want is, let me try to squeeze these 2 expression back in the expression of the energies and see what you get. Okay, so stick with those. So Ajahn, right here, omega a sine square, that's from the velocity. And then you say, I have a cosine omega t plus phi, that's for the x. Got that one? And then you square these 2. So what you're going to get is the whole thing right here that is written there. So you have 1/2 m omega square a square. That's fine, sine square. And the other one, you have 1/2 ka square cosine square. So I'm write both of these terms down here. Everyone follow the green box and the red box right there. So these are the components coming from the kinetic energy and potential energy. But then because we see the connections already that omega is square root k over m. So that means if I want, I can replace this omega square to be just the ratio between k over m. So I can turn this into a function of k. So this omega square is just k over m. And I can pull common factor because m will eventually cancel. So I get ka square factor on both. So I have whatever left is just only sine square plus cosine square.
Okay.
And that is exactly 1. Isn't that cool?
Okay.
I don't know if it's cool or not, but you guys know. Then you think about the mass on a spring. First thing first, if you want it to start oscillated, so you have to pull this one away from the equilibrium point, and that is your amplitude, right? So you just stretch your spring, yeah, and once you let it go, it's just going to take this energy here, because at your starting point, every energy that you have is in the potential energy, 1/2 Ka squared. U is 1/2 Ka squared, and that is your maximum, because that's your starting point. You stretch the spring out. You already sort of like collect all the energy, and everything is sort of put into potential energy, potential, ready to go, 1/2 Ka squared. But once you let it go, part of your potential energy will turn into kinetic energy. But from the conservation of energy, that's it. No matter when, no matter where, your total energy has to sum up to be 1/2 Ka squared, because that's what you're starting your energy from. Okay, guys?
Okay.
Cool. But the only difference is going to happen is just if you look on each individual one of them, if you look at the K alone, or if you look at the U alone, it's going to be a function of sine square and cosine square. So they are going to go back and forth, back and forth. Sometimes you get 100% potential, and once you let it go, there will be sometimes that you get 100% kinetic energy, and eventually it's going to overshoot, run into the other side, and the kinetic energy will turn into 100% potential energy, and the cycle will just continue on and on and on. So the simple harmonic motion in general is going to be the alteration between kinetic energy and potential energy. But the sum has to be exactly the original energy that you supply to the system. Isn't that cool? All right. So I think what you are looking at over here is you can analyze everything using mathematics. 100%. It's built into every mathematics that you can, answer to. Just everything just pop out from equation of motion. And this is why this Newton's second law is so powerful. From the equation of motion, all the craziness just lying in front of you right now.
Okay.
เฮ้ยไม่รู้ว้าวหรอกนะ but I think that's, I mean, to me, it's amazed me all the time that just a simple single line of second order differential equation, this is what's coming out of it. Everything. Crazy. All right. So this is my conclusion right here about the energy. All right. So now you can analyze this one in detail, that it's just the oscillation between kinetic energy and potential energy. But at any time, the sum has to be 1/2 Ka squared. All right. So I hope this slide will clear things up nicely. Any questions so far? So the way I thought like going back to mechanics, kind of like it's different feeling, right? In comparison to thermodynamics. It's like thermodynamics is more like, okay, this and that, you grab this, grab that. But over here is more like, it's different kind of analytics. I think it's just, okay, you go back to doing Newton's law a little bit. Okay. All right, guys. So just toward the end of today's lecture, I think this is the last slide of the day. And I think we'll have a chance to take a look at the exercises and everything. I will post some exercise for you to apply what we learned today into a real world, or it's not real world, but it's like a numerical problem and things on and on later. But I think something that is springing out from this is the case that you have complication from resistance or frictions. That's going to make more sense, because what you saw over there, that's just the indefinite oscillations, right? Back and forth is going to go on forever, which doesn't make sense. In real world, you will have some frictions going on, and it's going to, slow down the movements, everything just go down to zero. And that's give you another analysis that looks so cool. But we're not going to dive into detail too much, because that's, all right, it's more like we are taking like calculus 2 all over again. So we don't want to go that far. But the idea is this. So we can mimic that idea of having resistance or friction by just applying some friction to the moment, to the motion, like this. You have mass on spring one more time. but then you put the mass in some, liquid bucket or something like that. So every time that the mass try to oscillate up and down, the friction will take away the energy and everything will die off. Does that make sense?
Okay.
Okay, so you can do the same thing on the horizontal axis as well. If you go back to the original mass on spring over here, and then you can introduce the friction on the floor if you like. However, it's not a bad thing, but having a friction on the floor doesn't look as beautiful as what we are doing over here. So, I mean, the textbook is trying to come up with like a good exercise or good example for us to understand things. So that's why probably like some of you wondering, Ajahn, why don't you just introduce like friction on the floor and then you move on? The reason for that is having the friction on the floor just only give you a constant into your equation of motion. When I say constant, what does it mean? Friction is just mu times n, and n is just the normal force acting on this mass, and it's supposed to be mg, so it's going to be mu mg. So as you can see, this friction just introduce a constant into your differential equation. So what you have over here is it's going to be, well, you can solve for it. Everything will look different and it will take away some energy at a constant rate on and on. But then it doesn't look as nice as if you would like to introduce liquid friction. It's not even a word. It's a liquid resistance due to the liquid or due to the fluid. The reason for that is because they would like to introduce the friction that we just call it R instead of F. This one we're going to call it a resistance. And the reason for this is because we want the resistance to be a function of velocity. Isn't that cool? It's not just only cool, but it turns out this is more realistic scenario. Like when you jump down from the airplane, like if you're going to do like a parachuting or whatever, you jump down the airplane. You know that at first, you won't feel much of the resistance from the air because your velocity is still small. But then when you jump down further and further, think of it like an action movie when, the guy just jumped from the plane and they fight in the mid-air or the stuff. At first, the resistance is still small. But once you building up your speed, the friction will get higher, higher along with it as well. Does that make sense? Until it will get to a point where, somehow it's like, okay, your resistance, the air resistance is equates to the weight. And then you sort of like you're moving down with the constant velocity, and that's called terminal speed. When you jump down from the plane, eventually you will reach your speed will approach some maximum value because of the resistance is just exactly the same as your mass or your weight. Does that make sense? Okay, so that's why it's more interesting to look at the resistance that is a function of velocity right there. And the good thing about this one is once you have this, you can write this as, some factor. You can call it like a coefficient or something, but this term eventually will squeeze into your differential equation. And once you have this, solving this second order differential equation will look cooler. The reason it's cooler because now your second order differential equation will compose of this second order term, this first order term, and this zeroth order term. Isn't that cool?
Okay.
All right. So we don't want, but this is kind of nice because this system has this known solution to it. But as I said, we don't want to go too deep into it. But the final solution look like this, guys. It's so cool. It turns out it still have the sinusoidal effect inside. So cosine omega t, but that omega will change. Let me call omega prime plus phi. The factor of the sine and cosine, pick your choice. The components of the cosines, the oscillating component still there. But then it turns out because of the introduction of this resistant term, you will have the exponential decay in the front. All right, don't worry about the factor in the front, but let's say you have the exponential decay term in the front. That is good because that giving you the result that every time that you have this resistance, your amplitude supposed to reduce in time. And the reduction of that shows up in front of this solution right there. Isn't that cool? This is so good. So you can treat whatever the factor in front of the cosine to be your amplitude. That is a function of time. So over time, your amplitude will reduce and eventually will die down and everything will go to zero as expected. But there are some more into it. It turns out that omega prime will give you the, we kind of know omega is whatever in front of time. It's a factor that determines the angular frequency, right? But then because of having this term shows up here, there will be three cases. All right, I'm not going to dive into the formula of this one, but think of it logically, guys. Look at this. If things supposed to oscillate, so it means the fluid that this mass staying in supposed to be, well, not too thick. Does that make sense? So it means the fluid supposed to be fluid enough for this mass still be able to move up and down, but it's dying away, just like the upper right figure there. So if that is the case, we call it is the underdamped oscillation. The reason is we call damped because of this term right here. That is the damping. So things getting smaller and smaller. So that is a damping term. So we call this oscillation with resistance to be a damped oscillation right here. And because the fluid is still sort of like fluid enough, you still allow the oscillation to happen, but the amplitude is dying away. So this blue curve right there showing case of the underdamped oscillation. But then you can imagine there is another case. But Ajahn, what if the fluid that this mass is in is super duper thick? Whoa, it's like, once you let it go, you pull the mass down, let it go. It's just like, you know what I'm saying? It doesn't want to move. It's too thick. Think of it like you put it in like what? I don't know, something super, super thick, like honey, maybe something like that. Okay, something like, you know, glycerin. I don't know. All right, something super, super thick. Then what you get is the black curve over here. Once you let it go, it's just like, okay, I cannot oscillate for you to see. So this one, we call it an overdamped oscillation. It shouldn't even call oscillation whatsoever, right? Because I mean, there's no trace of oscillation for you to see, but that's what it means. The damping is just too great. So you won't see any oscillation anymore. What's my point? Jam. Okay, thank you.
Okay.
Very good, very good. Jam, that's sticky stuff. All right. Okay, so what's the point of this slide? The point is that it turns out there will be a borderline between you going across from underdamped to overdamped, or when you go overdamped down to underdamped. There is another fine line that sort of like break this two class of damping. And it turns out it's somewhere in between. We call it critically damped oscillation. So that means you can tune your resistance until your oscillation is just at the borderline between underdamped and overdamped. So it means you just sort of like, you know, adjust for the critically damped parameters and everything. But the good thing about this, look at the curve, guys. Look at the red curve. Can you see what's the benefit of this? The critically damped parameters allow you to get to the movement that from the starting point, it's try to reach your equilibrium the quickest. Isn't that cool?
Okay.
And that's how engineers is trying to do with like pneumatic or, you know, like hydraulic or whatever the mechanics that they are trying to design to damp any oscillation that happens. For example, whatever, if you have like a something that's supporting the choke up in your cars, for example, the spring stuff, they have to tune the stiffness of the spring. And this, the ideal scenario is that stiffness just hit the critically damped parameters. So every time that you drive the car, hit the roadblock or whatever, you know, have some bump and stuff, like your whole system can go back to the equilibrium point with the quickest and smoothest feeling. Isn't that nice?
Okay.
Okay. So if you have your spring in your choke up too soft, after the bump, you have to bump up and down a while before you get down to the equilibrium point. Or if it's like, you know, too stiff or what, I mean, I don't know, is it too stiff or too hard? But the idea is, I mean, if you, I think it's opposite, sorry. I think if it's too stiff, then you're gonna oscillate up and down a couple times before you down to the equilibrium. But if you have too soft, when you put hit a bump, then it just like, and then you just, you know, take a lot of time before it get down to the equilibrium point, something like that. All right. So it has the application in engineering and designs to tune the system to have, you know, some effectiveness in damping stuff. All right. So I hope I get you enough like relationship with what we learn here and something useful in real life.
Okay.
All right, guys, I think that is a good place to stop. And I think we learned so much today about it's analytical stuff, right? We don't do numerical at all today. But anyway, it will show up later, definitely. Next time, we're going to springboard from this and we're going to drag in the waves. By knowing this stuff, next time we're going to add another dimension to things, and then we're going to be able to understand how waves behave based on this oscillation. All right, but it's going to be double the fun and double the confusion, guys. All right, guys, so I think that is it for today. I will see you guys again next week. Yeah, all right, and we'll draw the conclusion about the dates of the exam very soon. Yes. Okay, guys, thank you.
Okay.
See ya. Oh, okay. For the earlier, okay. The first 4 minutes of class, we haven't discussed much. We just talk about the consensus on the exam dates. So eventually, I think we might want to go with the highest vote on there, which is the Saturday, 12th February. That I think the first 4 minutes will be that thing that we talked about. That's it. Yeah, about that. Okay. All right. Have a nice day, guys. Thank you. I'll see you guys next week. Bye-bye.